I take an immense pleasure in welcoming our guest speaker, Mr. R. Thirumurugan sir, Sales Development Manager Industry, Grundfoss Pump, Chennai. And is an experienced professional in pumps, having more than 20 years of experience in the pump industry. Sir has entered into the pump industries as a marketing engineer and now is playing an important role in this field as a sales development manager. So now I request you to deliver a technical talk on energy efficient pumps, sir. Over to you, sir.
Thank you, sir. Um, Good morning, one and all. I thank Dr. M. Venkata Ramanan and his team for giving this opportunity to present this wonderful topic, energy efficient pumps, in this forum. And I have some practicalities in which um, uh, any questions you wish to ask, you can just uh, enter in the chat box. And after the presentation, we will be having enough time to discuss on the questions in the open forum. So with this, I start my presentation. Okay. So about me, thanks, Mr. Sham, for the introduction. I am Thirumurugan Rajaram, and being in the pump industry for close to 2 decades now, worked with two major pump manufacturing companies of India. And yes, with all my travel, I could able to gain insights of pump applications in major sectors like automotive, power plants, the food and beverage, chemical industries. And yes, you can always reach me. I have my LinkedIn address for you. And I work currently for Grundfoss Pumps, Chennai. The prime agenda when this topic arises, energy efficient pumps, what came in my mind is like to talk something about the practicalities the entire globe is facing in terms of the energy crisis, and how the pumping system is related to it and how we can overcome it. So the idea is like to find avenues to improve the energy, the pumping system to an energy efficient pumping system, and what sorts of trends are evolving currently in the pumping system itself. So these content definitely will throw some insights on how the pump designs are being done, how the pumps are operated at site, and what would be the best way to operate a pump in order to reach the everyone's goal is energy efficient pump. Okay, so these are my prime topics I would touch upon. And one interesting is this industry 4.0. So that is a new trend where a lot of automations are evolving around the pump so that you can able to sense how the pump is performing in the situations. And I have a case study to just reflect how energy efficient pumps can contribute on the energy saving aspect. So with this, I get into the main topic. Why save energy? Because this is the biggest question, and every country will have its own goal. Whereas if you talk about Grundfoss, the India as a country, you can find the usage of or the consumption of energy various sector wise. We talk about industry or domestic or agriculture, and what we see, the industry consumption is very high. Obviously, the industry, we talk about even the main subject, what we have taken up is predominantly on the thermal power. So obviously, the thermal power is also a big consumer of energy, though for its own energy production. Okay, so obviously there is always an avenue within industry to explore and find ways to uh, optimize and also save energy. So the background on the necessity of all these forums evolve based on two things. One is like the evolving population, and that is tagged to the power shortage, and more urbanization. That is also a point we can see in terms the upcoming industries power consumptions, and the cost required to get anything. It can be building a factory or taking out the raw material. So what are maybe the cost has gone up like anything, and we should admit we have to be more conservative in terms of the energy usage. And overall, the main tagline we can always keep in mind that global warming is also a situation where unprecedented natural calamities are getting impacted. So that also can be tagged to why we should save energy as much as possible. And again, basic guidelines where we see like for 1 megawatt, the cost of investments, we can say for a plant would be around 50 million Indian rupee, and whatever you save is equivalent to saving 2 kilowatt at the generation point. So that is the background where you see a lot of transmission losses, a part of this energy supplies. So saving is always the best thing in our mind. And with the scenarios of the fuel, whatever fuel which we use, it can be oil or coal, so gas based. So whatever might be, there is always a kind of a shortage going to evolve. That's why you could see a more adaptation of renewable source, like it can be wind energy or solar, or very less consumption of fuels based generations are happening. So the necessity is must in the current scenario, and we should find avenues for it. So on the pumping background, what we see is like uh, if you connect all the population of pumps across the globe, you could see the 10% of the globe energy consumption is just fed into the pumps, which is used for various application. It can be used for your house, it can be used for your municipal transfer, or for the industries, or for any treatment plant like that. And what statistics talks about is like 9 out of 10 pumps operation are not optimized for that applications. Therefore, there is a waste of energy is being identified. And what we find out how these 9 out of 10 are being identified at site. Okay. There can be a lot of factors connecting why it is not being optimizedly running at site, or why it is inefficiently. We can also put a word inefficiently it is being done. So the goal is like to save as much as energy at the pump, so that your cost of operation also comes down. When you touch upon the cost part, obviously these are just thumb rules, but it will vary from industry to industry, you can say, where in which the initial investment cost is just 5 to average, I could say 10 percentage, and then comes your energy cost and your operating cost, where in which the whooping maximum would be your energy expenses, in which for what you pay. And obviously there is always a rise in the energy price over the last 2 decades. You can see the amount of energy cost has, I could say, almost doubled in some countries. So it always um, we have to find ways to optimize the energy uh, at the consumption point itself. One more statistics, just to reflect how the efficiency is so important in the current times. This is one interesting statistics. What could reflect is like if the entire globe is being switched to an high efficiency pumps, almost we could save close to 4% of the world electricity consumption, and it can able to fed close to 1 billion electricity the residential electricity consumption for the 1 billion people. So yes, there are areas where you don't see much of energy reach, we can say. So maybe wherever we able to conserve, and yes, there can be a better utilization at some points. Okay, so the idea of all these things is curtailed to giving a benefit for any users in terms of how an energy efficiency improvement impacts its entire operation. So one is reducing the operating cost, in which the energy cost or the related maintenance, everything can be curtailed. That impacts on its profitability, and also help him to stay competitive in the global market, we can say. So cost uh, is also a very prime factor for survival, and obviously this energy efficiency improvement reaps a lot of benefit for any users. So now we are just entering into a point where how we can able to find a pumping system is inefficiency. Then two things: either you can correct the system, or you can adapt for a better energy efficient system when you go for a new procurement. Okay, so this is what people look forward. Okay, whenever you are in a position to buy a pump, it can be for your resident or it can be for the plant, whatever it may be. So people have two things in common. One is like whether I want to go for a very cheapest product or I want to go for a most efficiency product. Okay, so when you could see almost 85% of your energy efficiency, the life cycle cost is only spent on the energy consumption of that product. So obviously, going for an efficient pump makes sense, when which you can save that 85% cost, maybe related when you approach a energy efficient product in that place. So it's always better to procure a product based on the efficiency, not much aligned on the budget levels at the current scenarios. Okay, so the some factors, like when you find there is an inefficient pump, obviously that is a tag to your power consumption. So now what would be the reason for excess power consumption? So for example, you have a pump and it is 11 kilowatt, and you see the energy consumption is close to 10 kilowatt. So now you can find out what would be the avenue you can save power in that particular product. Is there any viability is there to save power? And if it is some extra some factors we can able to overcome, definitely we can able to arrive that. Okay, so the major factors we need to talk here is the improper selections. How a product is basically selected in place. So what would be the selection criteria here? Because every product is having a kind of a performance characteristic, and whether we are reviewing the characteristic to full extent to get a feel that the product what we are giving is the efficient product. Okay, and second avenue is like old inefficient pumps. So we have come across pumps which are running almost 20-30 years at site. So imagine the pumps are running. Obviously, the accountability of wear and tear is also need to be considered, because such a long duration will have a lot of wear and tear, and obviously the reduction of efficiency would be immense, we can say. And we have come across sites in which your initial efficiency would be 80%, and obviously over a period of time it can come to even 50 to 40% efficiency also. That depends upon the wear and tear and how the condition of the pump is it. So old any pumps for our understanding. Anything above 7 years, we see it is a little bit as almost reached, I could say, almost it has reached 60 to 70% of its design life, you can say. And then improper layout. So the layout also need to be understood. So because the pump is not just going to transfer a water from a point A to B. So now we need to understand how there is the pipe routing happening between point A and point B, and how much of friction loss is coming into picture. And second, the piping plays a important role to make the pump efficient to some extent, we can say, like, because when it is giving an opportunity to to make an air entry, obviously the pump will definitely try to deliver both water and air to the source, and obviously the pump will not perform. So piping also plays a vital role here. And second, the important point is over design, because in many industries, what we see is like hello, yeah.
No, no,
So
sir. You can
yeah,
continue.
okay. So on the over design point, if you take an industry which having an ambitious plan to expand later date, but if they have accommodated something on the pumps for the future also, but they would be operating at maybe partially open or 25% open of the discharge wall, definitely we can say at the moment it is an over design, because it is not going to support for the current situation, and obviously it will be operated at very low efficiency. So these points we will just elaborate in the coming slides. Okay. So
Madam, faculty phone la
so the major one of the major reasons for excess power consumption is getting to know what product you really want. So this is a kind of a situation when you get into buying a product in the market which is too identical, but what you will prefer. But the preference comes into XYZ factor, whether it is based on the performance, or maybe if you take a car, you talk about the mileage, you talk about the pickup and also load carrying capacities, or you want more style, or you want more terrain based operation. So the preference should be there. Okay. And also to operate, first of all, to operate a product for its design condition, um, that helps the pump to be operated at its full efficiency conditions. So let me take a simple example here. So what you have is a simple a diagram, a small P&A diagram, where you have a pump. Um, it is getting into a machine kind of situation. It is a closed loop. Okay. And you have a throttle valve. Okay. On the discharge side. So you have a suction, a discharge, and you have some gauges to measure your suction and discharge pressure. And this is your performance characteristic of any centrifugal pump. So what are being plotted in a curve is your flow versus head. You have the flow in your x-axis, head in your y-axis, and you have the efficiency of the pump on your y-axis on this side. And same, you have your power consumption on your y-axis and your NPSH. So NPSH is your net positive suction net that is required, or the value is been a design value for any pump manufacturer. So in this case, important thing is your power consumption. Okay. So what you could able to see is like a pump is being designed. This pump is being designed to operate between, for example, this is 50. You can talk about 61 is your maximum head, and your least head is close to 33 meters would be a least head. And same thing, your power condition also. So from the flow condition, maybe from 10 meter cube, it can go up to 80 meter cube. So this is your boundary limit for this particular product. Now within this flow and head boundary limit, your power consumption will keep on increasing whenever you increase your flow and the flow parameters. And same thing, your NPSH keeps on increasing. Okay, and same thing, if you see the efficiency curve, it will rise to the top where this particular point we call as a best efficiency point. After that, it just maybe becomes flat, or it will be it will be just drooping to the end of the curve, you can say. So this is your basic characteristic, and whenever you want to buy a product, we insist to have it very close to the best efficiency point. So if you select a pump here, uh, obviously the efficiency is good, and obviously your energy consumption will be slightly lower. But if you select a pump maybe somewhere here, obviously you can see there is a drop in efficiency, and that impacts your energy consumption also. So understanding the curve of all the product helps you to understand its performance and arrive what is really required in this case. Okay, so maybe I just briefed you about the performance curve. Some critical points. The last point where your head curve we call as shut-off head, and this curve where you get maximum flow we call a runout condition. And on the efficiency point, we can say BEP would be a best efficiency point in the curve. So the main guidelines is um, say on the left side of BEP, you can travel up to 30%. Maybe within that zone, your selection is okay. On the right side, maybe another 15% would be the extended zone wherein you can able to do a selection. So it is not advisable to go on the left side, say 50%, because we can say as non-stable operating zones for the pumping system. It can have mechanical issues over a long period of hours operation. That also an impact of underutilizing a product, because you will have a bigger pump that for in which you are just trying to operate for very low duty conditions. So I said like correct selection depends upon the efficiency also, because currently in the market you can find a lot of types of product, the vertical orientation, horizontal orientation, submersibles, a lot of types of product, and we need to be very cautious in selecting the right one where you find more efficiency on the product. So for example, I have a curve for a duty condition of 45 cubic meter at 72 meters. This selection for a particular model comes close to the best efficiency point, and your efficiency 76%. And this is a vertical type pump, vertical multi-stage pump, horizontal means the surface mounted version. Whereas if you talk about an horizontal version pumps for the same capacity, but the head is very high. So in this case, you can find the efficiency is close to 64%. So obviously, this impacts in your energy consumption. The efficiency drop itself close to 8%, and also your energy consumption of this pump would be much higher compared to this product. So understanding the efficiency and correlating with the energy consumption of the product, that helps you to helps you to know how much of energy you could able to save here. Okay. So the idea of optimizing the pump operation based upon the performance curve is due to these factors. The one we touched upon here is your best efficiency point flow, because this is your ideal zone for operation. So the one which you could see, the green one, what I have been referring, so close to 30% from the BEP on the left side and 15% from the right side. Okay, so from the top we can say when you have a shut-off head operation, which is nothing but very close to your zero flow situation, that will have very high amount of heat getting generated because of thermal minimal flow situation. Okay. And second, if you are operating not so close to shut off it, slightly away, you will have a noisy operation, cavitation surge, high vibration can be a situation. These zone will find avenues for your the rotating parts like your bearings, mechanical seals. So those can have an impact on its life because of the vibration and the noise levels. So this is your low flow limit, in which you also need to have sufficient amount of flow getting into the product to avoid the cavitation and wear and tear. And yeah, so we have this minimum continuous stable flow and intermittent minimum flow situations and thermal minimum flow. So the diagram itself tells you what would be your ideal zone to operate. And you have suction impeller, shockless entry situation, and cavitation and eye vibration. Because here you find when you are operating on the close to your, I can say, right hand side or the end of the curve situation, your NPSH will be higher and your energy consumption of that particular pump will be much higher. So everything will be in a stressed situation where in which it will initially cavitate because your NPSH required will be very, very high, and in turn it can not able to suck the take out the water very easily, and that will have an impact on vibrations, and obviously that impacts all your rotating parts, mechanical seal, your bearings and other parts in it. So that will seriously have an impact on the pump performance. So in terms of your excess power consumption, this is one site wherein which you could see split case pump having a suction and discharge, and what uh, thing we could able to identify here, it is like you can find both your suction and discharge valves are being throttled. So meaning they are having a oversized pump and trying to throttle the situation and try to run it. Obviously, this will not help to have an efficient operation, and also having a more service related issues on the product itself. Okay. The other factor is your old and inefficient pumps, so which I just touched upon, where you can find in any power plant, obviously, which is where in India you will find almost 30 to 40 years old power plants also, where they are trying to adapt the energy saving mode. Definitely we could see a lot of avenues there because of old pumps are still being operated at certain sites. So this is one thing we could identify in an industry where in which the pump was 20 years old, is a vertical turbine pump which is close to 25% efficiency. That is what we could able to identify. So there is a lot of scope when you talk replacing old pumps. Your what you said, the energy saving potential is high, and related the investment cost, because when you talk your return of investment, the time taken to take out your investment cost will be comparatively very, very fast. Some more points for you to note here is like the piping part also influences your pump performance. That impacts your energy efficiency. So here you can find this piping is a kind of a concentric design with the bottom flat. So that helps you to have an air pocket because of water level difference. So in this case, you can find this is an suction discharge, means it's a suction side adapter, where in which to have a mating of your pipe and your pump flange. This is being used, and this particular design will facilitate an air pocket always. So that helps the pump not able to perform to its situation. And this can be corrected with this kind of eccentric reducer situation, where in which always the water is filled in this particular zone, and yeah, whenever the pump starts or stops, will not have a point of air entrapment in your suction or in the pump itself. Okay. And in terms of your velocity guidelines, because when you talk about the hydraulics of the pipes on the suction discharge side, obviously the recommended velocity has to be maintained so that the required pressure is met. There are sewage pumps or the dewatering pumps and all, which need a minimum self-cleaning velocity, so that at any point of time the sludges or whatever particles doesn't settle in your pipes. So certain details like your velocity makes a very important role in designing your head required at your site based on the layout. Okay. The other diagrams wherein which you can find the suction side for split case pumps, how it has to be maintained. So you should have a flat top on the flat top, and if you taking this one is your negative suction situation and this one is your positive suction, so accordingly you can able to design your eccentric reducers. Okay, so over design is also one situation which just I briefed, when which the situation has to be very apt for the current working conditions. So whenever people buy a pump, calculating the flow required for the future, but people, if not in what is it, concluded their future plans very soon, maybe not more than 2 years we can say, but still there is a lot of energy wastage in the product we can say. So that can be completely avoided and designing it very apt for the current situations. Hello.
Abhirami.
Hello? எவ்வளவு மாம்பு இருக்கு?
Participants, please mute yourself because it is disturbing.
So we have just touched upon some of the layouts on other situations. Now we can see how the pump is being operated at its site conditions. Okay, so what are the situations currently? You can see throttling by a wall, like you have a discharge. On the discharge side, you have a throttle wall. So people try to open or close based upon your flow required. So this was been practiced for a very long years, and even in very old industries, you can still see throttle wall getting opened or closed based upon your flow required at site. Okay. Bypassing by a wall. So this is a situation like whenever there is excess flow, people try to bypass it with a wall. So meaning that that flow will again go to a tank, but still the pump is going to say develop for its 100% requirement. So say for example, for the 100% flow coming from the discharge, and you could divert or you are going to allow 80% to your system, and that 20% is a wastage. So again, it comes to your tank or your system, but energy consumed is for 100%. So obviously that is also an energy killing situation. On and off control method is like just to start and stop whenever there is a power required, the pump requirement arises. So this is also will have high starting current situation, but still compared to other throttling or bypass, this makes little bit energy efficient we can say. And the foremost energy efficient system will be operated on the variable speed control of the pump. So it is nothing but a VFD, which helps you to control the speed of the motor. In turn, the motor will reduce the pump speed, and obviously the pump will deliver the lower flow or rate. for the situations. So this method, variable speed control of pumps, is being adapted in many industries. So now you can find large pumps also getting adapted for a variable frequency drive operation. That makes sense because your energy saving would be high, because any product is not it is not going to operate it for full load situation. And if you talk about the current pandemic itself, like how many industries were running full load? Obviously, very few industries we can say. Maybe pharma can be one industry running 24/7 and that situation. But many industries were running at a very lean load. We talk about 10% to even a 50% load scenarios have seen. So for that situations, you can try to have if you add the variable speed drive situations, obviously your demand can be accurately met for that lean demand, and your energy saving. So that time your energy cost will not be very high. That would have taken your profits much. Some situations, what you could see is your parallel and series running of pumps. So this is what you could see, a parallel running pumps, where you parallel pumps will increase your flow. So if you have two pumps and each pump running for 100 meter cube per hour, at your discharge in a common manifold, you will get 200 meter cube if two pumps are running parallelly. And if you talk about a series pump, which will increase your head of the pump operation. So for example, you have a pump generating 10 bar pressure, and it is seriously connected with another pump of 10 bar generating. So at the outlet of second pump, you will get 20 bar generated liquid. So which can be used for high pressure applications. Okay. So what we identify, the variable frequency drive operated pumps are energy efficient, and not all customers would intend to have a variable frequency drive, but that adaptation is slowly picking up in many industries. New age industries, we can say, are already into that and trying to accommodate because they can optimize at the initial level itself. Whereas if you find a pump which is quite old and you want to reduce the flow unnecessarily, which is not required for the site condition, there is also one method you can able to do it is trimming your impeller, because impeller is one component that is designed to generate the required flow and head. So once you trim this impeller, so it is nothing but you are trimming this diameter. Say I have a 300 dia impeller and I want a reduced flow, you can just calculate based upon this formula, based upon the diameter for the full load and what is your head required and what is the current head, what is the flow and what is the required flow. So based upon that, you will arrive this dx. So that is your trimmed impeller diameter. So now you can design or you can just trim the impeller so that your pump will have the reduced flow, and that will also impact your energy consumption. So in this case, you can see a small one level of will have an impact on your, say if you are reducing your head from 70 to 55, obviously the impact on energy from 100% to 67, almost 33% of energy consumption is saved with this way of operation. So this is also a method you can link on how to optimize with the current resource itself. So the idea of all this thing is tagged to the basic law, the affinity law, which is well known, which is widely used in pumping applications. So this defines what is the impact of flow and head with variation in speed, that is flow variation, your power, your the pressure variation, and also your power variation. So, so the impact of reduction is reflected 3 times on your energy consumption. So that is the purpose. We always insist to go for a speed control approach wherever possible. So you have this point, the flow decrease proportionally to speed, the head decrease by second power, and your power consumption decrease by third power. So this is your true impact, which helps you to save a lot of energy whenever you want to operate the pump at lean loads. rather than adapting the other options like control wall or bypass wall or other situations. So in terms of energy saving in pump applications, what I could able to reflect here is like you can find a fixed speed with a throttle wall. For example, you are trying to operate here and with a flow of, say, example, we are talking about 80 meter cube, and suddenly your demand drops and you want to operate at 20 meter cube, the system will operate at this head. So where you can find this would be your excess pressure getting into your system. First of all, like your system is been designed for handling this 3 bar, but unnecessarily you will be giving a 5 bar pressure into the system. So this is your excess pressure will impact a lot of things in terms of wear and tear in your pipes. It can impact on your head calculations. And moreover, you will end up in a very low efficient operating things. But if you adapt that by removing a control wall and trying to adapt a frequency drive, where in which based upon the input it is going to operate, here you can find you still maintain the same 3 bar pressure. There is no excess pressure. You can move from a nominal flow to a reduced flow very easily and try to operate. So this will impact a lot in terms of energy consumption, and there will be a lot of potential for you to save energy in this aspect. And automation becomes a very prime adaptation in the current scenario, where in which you can take a feedback from a sensor and you can have some set point in your controller, and that will try to match the set point regularly. So the sensor feedback will help the pump to correlate with your set point and then try to alter the VFD speed in terms of the motor speed, and in terms your pump rotating speed also come down, and it will be continuous. So irrespective of the situation, the pump is going to adapt itself for the real time situation. So meaning even your load at a particular date is 10% to 100%, the pump is going to respond for the load situation. So end of the day, having a fixed speed pump, say running, say if it is consuming 10 kilowatt and you are running 12 hours, 10 into 12, 120 kilowatt would be your final power consumption for one day. But with a VFD, obviously there will be an impact. Even we can say from a minimum of 10% to a maximum of 30% would be the your energy saving potential is available here. So in terms of the pump application, I just touched upon the lean loads, because even in a factory you can find whenever there is your people getting in and the water consumption starts and it becomes low till your time for lunch, and maybe there can be some consumption, and again when people going out of office there can be some consumption. So likewise even for different process cycle also, for example, if there is a rubber production in or a situation where the production is happening for continuously, there can be some energy consumption, and if it is for 50% load, there can be some consumption. So there is no flat scenario of flow consumption. So it is keep on varying. So what we can able to adapt here is like to have multiple number of smaller parallel flow applications, the parallel flow applications. So this will help whenever there's a lean load, either one pump can operate, and whenever the load picks up, the second pump also keep operating. So at any point of time, your pump efficiency would be much higher, and your energy consumption also will come down. So these kind of parallel operated kits are being offered. Maybe in power sector, we are given for hydro pneumatic booster systems for drinking water applications and for transfer applications to your various utilities. So these and all will help in terms of energy optimization. So this is one more option. Yes, VFD required is now mandate. So people advise you to go for a VFD if it is a lean, it is a where you have a fluctuating demand cycle. But there is also one more concept you talk about multi VFD. So multi VFD situation is like you have three pumps. Instead of having one VFD common for all the three pumps, and we can move for one individual VFD for each pump. So there will be some increase in your capex, but the impact of your energy saving is very, very immense. And whatever you have invested on excess, you can take it within 2 years time period. Okay. So one thing is this is a single VFD concept. When you compare with a multi VFD, obviously you can find your energy difference in these two cases. It is much higher for a single VFD and is very lower for multi VFD. And second, you can find the multi VFD will have a very smooth operation in terms of your pressure buildup. So there will not be any sudden surge in your lines. It will be very smooth ramp up and attaining your required flow steadily, we can say. So that and all you can able to avoid in this case. And also the efficiency, when you compare your efficiency, and you can find this efficiency is much better for your multi VFD, and this is what your single VFD. So whenever your vary flows picks up, the efficiency is low, whereas here we try to maintain the same efficiency in your multi VFD options. So the adaptation, when you design a system for any water distribution application within the thermal power plants, adapting a multi VFD system makes a lot of impact in your energy consumption. The impact is not seen on the surface mounted pumps. This is also visibly seen on your submersible dewatering pumps, because in any power plant you can find at least hundreds of submersible dewatering pumps here and there, like to dewater liquids, dewater your flood dewatering is the situation you can able to see, or pond dewatering, or to pump out sewage from one place to another place. So the challenge is like on and off system operations will because here this complete scenario is going to be worked based upon your level, that is your water level within the tank. So when you have some automation where you can find a float level in the tank, and when the float level reaches, the pump will automatically start and stop. Okay, so even for the submersible dewatering pumps for wastewater applications, adapting a VFD makes more impact on energy savings, because you will not have end up in getting into higher head scenarios. You can precisely operate for your required duty point. So here you can find the 100% duty, you can able to reduce to 87% of your frequency, and obviously that will impact your energy saving on your wastewater applications. So two things, the pump speed also will come down, and second, you will have very lower velocity in the pipe. That also increase your life of your pump, life of your pipes. So these two things, and over and above, you have an energy saving option in this case, because here the system is responding truly based upon your inflow demands. So whenever your demand is very low, or whenever your demand is very quick, the pump also should respond very quickly to take the water out. So that scenarios we could see much in your rainy times, where your inflow is very fast, so the pump has to respond very quickly, and the lean time it can respond very slowly also, we can say. So maintaining the required velocities in your pipeline. Yeah, so this is a comparison between on and off control option and a speed control option. So the resulting kilowatt, you can find almost we have a huge potential in terms of energy saving. So in on and off control, we are talking about a consumption of 15.6 for this duty condition. With a speed control, obviously these pumps can be operated at the required duty point, because the biggest point with a clear water pump and a wastewater pump is like the wastewater pump is designed to handle more solids. The preference is first to handle solids in the in the wastewater. Okay, so these impulse trimming is little bit challenge in certain designs. So not all wastewater pumps can be easily trimmed because that will affect your pumping performance also. That can avoid taking out solids, and that can be settlement of solids in your tank, and sludge formation in the tanks becomes a big challenge than pumping itself. Okay, so now we touch upon the application. So where we stand here is like when you get into any thermal power plant, we have very large centrifugal pumps. We talk about maybe in megawatts also the pump capacities, and then you have auxiliary and main cooling water circulations which are getting into your cooling towers. And if you have a water treatment plant to treat all your water, whether you take it from the river or you take it from any pond or any storage, and then obviously there will be a treatment, desalination plants, and obviously all these applications you will find a lot of pumps. And I'm just giving an indication where you can find much avenues within a plant in terms of energy savings, because the bigger ones stay here, the raw water and cooling tower, because these are always demanded for high efficiency, and people insist for 80 and above percentage efficiency pumps because that consumes at least I could say 60% load of your energy demand for pumps within the plant, and rest would be a smaller capacities where your kilowatt would be say less than 200 kilowatt and below. So that will be used for all your auxiliary needs in your power plant. But still, even a small change from 7.5 HP to 5.5 HP, that also makes an impact, irrespective of what might be the application. Definitely, you can able to find avenues here. The one which I mentioned, the dosing skid system for chemical dosing. Here we talk about the energy optimization in the centrifugal pumps, whereas in your dosing pump, the chemical optimization comes into picture. Because when you talk about the tariff for energy, maybe 7 rupees in India, whereas if you talk about the chemical cost, maybe that will vary in thousands. Even a 1 liter or a 200 liter can, whatever might be the cost is very high, and we are not going to leave that also, like until you do a precise dosing, then the things you will have a lot of avenues to save it. Okay, so when we touch upon the pump set, obviously the motor plays a very vital role because the pump designs remain same for n number of decades. It will take its next version 2.0 or 3.0, maybe with a lot of detail engineering and design and development. Whereas the motor market is wide because not only pumps use motor, you have fans, a lot of other equipments. Even our automotive starts using motors nowadays. Okay, so we have the motors classification. We have this 1999 classification talks about the motor efficiency ratings are EFF3, EFF2, EFF1. The EFF1 would be the higher efficiency motors. Way back in 2008, that was superseded with a number digit from starting from IE1, IE2, and IE3. So meaning the IE classification motors are coming up into the market, and it is almost 12 years now where you don't find any EFF motor for the new requirements. And the motor, what we have, the highest rating available in the market is IE4, which is almost curtailing out a lot of efficiency into the motor. Sorry, a lot of losses in the motor, so that your efficiency will be close to 94% efficiency also. I hope my previous session, Mr. Srinivasan would have touched on the IE classifications and the standards what we follow in the motor. And this is an international standard. where Indian standards also available, meeting the IE3 and IE4 norms. So what we see is like there are many plants, many power plants still using this EFF1 or EFF2 or EF, maybe non-listed motors also there in existence. So there is a huge avenue for the user to jump from this to this, either IE3 or IE4, so that sustainably there is a improvement in your energy improvement goals. So making your plant more sustainable and maybe energy saving will always improve your operating expenses, we can say. So what is there available now is your IE5 efficiency motors. So we Grundfoss also having this IE5 efficiency motors, and slowly the market will move to this norm. Maybe in a decade time, I could see the adaptation of IE5 becomes a new normal, we can say. So in which the motor will have its own integrated VFDs and everything put together in a single box. So it's like you have a smartphone with all the apps which can give you all the data regarding your health, regarding your investment, banking, studies, education, whatever might be. Likewise, this product is going to throw about the scenario of the product in terms of its performance, in terms of its reliability, in terms of its operating situations, how healthy the product is. So that level, the product is going to reflect its status, we can say. And when you see energy efficiency in the motor, how much it has been increased or improved over a period of time. Okay, so or within IE1 we have IE5, and you can see this is the leap from 84% efficiency, almost I could say almost a decade before we have this IE1 norms getting into the market, and straight away we could adapt IE2. From IE2 we have almost 5% increase in efficiency. So there is a lot of potential in terms of saving energy, just replacing motors also, we can say. And other avenues, maybe energy audit is an important tool. Nowadays, people look forward to adapting energy audit because all thermal power plants, I am sure, will have an energy audit energy team which audit all the pumps and other accessories, and then give a feedback on the potential in terms of saving the energy in a particular product. On the pump side, energy audit can be done based on the situation. We can able to measure the flow, what is the power consumption, what is the pressure. So we will calculate the real-time data, and then we can able to arrive a report stating what is the current efficiency and what best you can able to go when you go for a new product with improved efficiency and what is the investment. So this kind of an approach will help you to understand the current efficiency and what is the energy efficiency improvement you're going to show, what is the energy saving, what is the investment, what is your return of investment. Okay, so and the end, how much of carbon emission you could be able to save here. So such level of approach is there in the market where people try to optimize your CO2 emission in any industry, because a power plant would be the highest producers of CO2, and obviously that also can be curtailed when you start looking of these approaches. I hope there are some questions with all these slides for you to just get clarified, because I have another maybe a 10 on odd more slides because it's almost a 1 hour gone with our session. Yeah, Shyam, is it going on well?
Yes, sir.
Yeah, thank you for it. And yeah, so in terms of the approach, this is some interesting fact for all industries to have a look. How much of evolution happened within the industries. So those days people look forward of better maintenance, installations, better efficient or better size pumps. So when we go adapt all these options, maybe put together maybe a 10 percentage put together itself, we'll end up in having a 10 percentage optimization is possible. A better system design is one thing. Any pump is not going to work independently. Okay, so it is going to be part of a system. So you talk about a boiler feed, it is part of a boiler. Like you talk about an condensate extraction or whatever might be, like it is going to be part of the system and it has to support the system first. So once you design the main system, and obviously the sub systems like the pumps and other things will be well optimized, we can say. So that yields close to 10 percentage energy optimization or payoff, we can say. And the foremost optimization is your better system control. So the approach which we already talked here is your VFD based pump operation. So almost 20 percentage of your or close to that, we can say, benefits you can able to get with a better system control, like moving from a fixed speed or on and off or from single VFD. So moving to this approach, obviously, and also system control is nothing but not just a pump going to run. It is going to run in synchronous with your situation. So whether you want a 4-bar pressure in your line, the pressure transmitter will always sense that and give a signal to the pump so that that scenario will always be maintained. The same thing if you want to have a delta T of 5 degree in your cooling tower, we can have a temperature sensor and then can able to operate the pumps based upon the temperature sensor. So likewise, all the products are now can be linked to better system control options. And obviously this industry 4.0 revolution also talks about that, because this is also getting into many industries. Even power plant is also a point where a lot of automations are being done already inside. So obviously these pumps also can be automated so that more adaptation on understanding the pump performance, reliability, and availability is also makes important here. So the speed control helps you to reduce your life cycle cost, your CO2 emission, and reduce noise from installations, no water hammering, adapts automatically to changes in system. So that is so important because, as I said, the peak demand is not always there. So there is always a seasonal changes, and obviously the demand also fluctuates in any industries. So adapts automatically to changes in system. Speed control pumps can make some walls, etc. unnecessary, because unnecessarily you can avoid an wall at your discharge because you're not going to throttle the discharge. So now the VFD is going to take care of the pump speed fluctuation. That is also possible. Reduce installation and commissioning costs, because in some case we can find the installation of multiple things can be avoided, and having a single entity, having a pump, motor, VFD, controller, everything will makes more sense, more energy efficient also. And speed control reduces more stress on the pumps and pumping system, because no excess flow at all point of time. Relevant flow and head required comes into picture. A lot of productions are being there, like in motor productions, thermal overload relays, everything is there in the product. See, the idea of system-based control is like identifying for what application, what kind of sensors are required, and how you are going to configure your controller to work upon. So once you have a proper programmed proper programming, so that it will help you to optimize your entire operation itself. So based upon your application, you can able to design whether this pump can be operated on PT or a DPT or a flow meter or temperature transmitter. So even for over a tank filling, what would be your optimized way? You can have a level transmitter, start and stop based upon the level, or if you are draining out from your overhead tank to getting into your system, you can also use a level transmitter. So such understanding how you can automate makes a system more efficient, we can say. So now we touch upon some of the products in the pumping application, like what pump uh, is available and what where you can use this, and what would be the recommendation. Okay, so in terms of pump types, in the centrifugal category, we have this inline single stage, horizontal end suction pumps, and horizontal close coupled pumps. So I think this one would be predominantly seen in your water transfer application in even MCW, ACW, or auxiliary pumps or DM water transfer. Many of the pumps will be horizontal in section. So what we could see here is like your impler, you have a shaft assembly, and your bearing housing with your drive end and non-drive end bearings, and you have a stuffing box. Inside a stuffing box, you have a mechanical seal. So whenever you have an issue because of cavitation or because of excess vibration, pump not operating at a particular zone, what hits first is your mechanical seal and bearings, because these are very, very sensitive part in the product that can easily get affected. So always we recommend to operate the pump for its intended purpose, intended operation situation. That is more important. Okay, and after that you have a coupling and a motor. Obviously, this coupling is also a sensitive part where your coupling life also affects based upon your situation. So that is also an important thing to get noticed. And here you can find there is no coupling, but still there is a stub shaft with a shaft arrangement. It is a close coupled. You are eliminating the coupling need. You are eliminating a bearing need here also. So these designs also been adapted in power plants. Here you have a horizontal multi-stage version and vertical multi-stage version where you find more pressure is required to transfer the liquid. So for example, in water treatment plant, you need a high pressure pump before your RO membrane, and your pressure is 15 bar to 30 bar pressure. The same thing, your initial horizontal multi-stage pump, which is acting as a feed pump before your or raw water feed pump, you can say, in your water treatment plant, which maybe 2 or 3 bar pressure it can able to operate. And these are submersible borewell pumps. And if you have a lot of borewells for water intake application, obviously these submersible borewell pumps are multi-stage, which can work, say, even up for close to 30 bar pressure operation also. And of course, there are very large vertical turbine pumps, mainly used in MCW, means your raw water intake, and even for the large cooling tower application also it's been used. Okay. And then your split case pumps for large flows, say up to even 10,000 meter cube capacities also, you can able to offer these split case pumps. And one interesting aspect in the design is like you should consider this double value design, which will eliminate the axial thrust happening on the impler, because that will avoid the proper rotation of the impler, and wear and tear situation can arise. So there is double value design is a common one in all split case, which can be taken up here. So some designs reasons for having double volute instead of a single volute. So eliminating the radial loads by balancing the hydraulic forces of the liquid within the pump casing. So this enables more adaptation of running the pump at the designed parameters. So once you eliminate much of a radial load, that it is almost saving a pump internal parts from any damage. Okay. So we touch upon the shaft seals. Obviously, you will have a lot of pumps running with shaft seal, and also with gland packing. because in older design pumps, you can find these gland ropes being installed as a packing on the between the ceiling of your pump and your shaft area, and there will be a leak because when you have a packing, it has to be, it is a kind of a nylon wire where in which you need to lubricate that with the water, so it will lubricate and it will create a leak. Okay, but if there is a wear and tear, there will be excess leak, so that will pollute the surroundings, and that can be an hazard also in terms of the environment itself. So always adapt mechanical seal in all your pumps, because mechanical seal improves the efficiency of the pump. It will avoid water wastage, and in turn you will have a better efficient pump also. Okay, these seals will not fail until or unless you have situations making it to fail. Okay, some situations you will find dry running, so that will have an impact in your pump operation, because once your suction is completely choked, clogged, okay, footwall got failed, dry running situation happens. High or low pressure or high temperature, because these seals are temperature sensitive, pressure sensitive, because the seal is designed for 16 bar. If it is been mistakenly operated for excess pressure, seal will fail. And abrasive parts in the liquid, because all these pipings are being welded before it is completed. So there is always a chance a lot of impurities like some metal particles being present. So what we insist to thoroughly flush the lines before the pump is installed, so that that impurities will not get settled in the mechanical seal in the operated pumps. And last one is your wrong configuration of the shaft seal. Maybe your seal or sealing surface, if improperly designed, then you have a chance of a seal failure. And some more efficient way of operating pumps is like mounting the pump at proper on the floor. Okay, so there are different design criteria for different situations, from a normal floor mounting, and you have a plinth. So obviously the recommended one would be from here, from the plinth, where with the proper foundation and with the bolts arresting the pump movement at any direction. Okay, and also where there are situations, excess vibrations that can penetrate from the instruments or the machines which are very nearby to the pumps. You have vibration isolation dampeners or vibration isolators, where you can able to still safeguard the pump from excess vibration from the nearby machines, we can say. So in terms of pump installations, what we can see is like the piping on the inlet side of the pumps. So this kind of inlet pipe always what happens, there will be always a chance of water air entrapment. Even if there's an obstruction, if they put it above, there is always a chance of air entrapment when the pump stops or situation. And you should always have a bottom face on the top. So here also a situation you can find the air entrapment happens, and suction will not happen here. Conditions. The same thing, you're taking a suction, the situation of air entrapment will reduce the pump performance. Okay, so some kind of a baffle arrangement will help you to avoid any water turbulence getting into your pump inlet pipes. Okay, so this kind of baffles can be helped. Slightly enlarged pipe openings on your suction will reduce your velocities, and smooth entries will be there rather than having a flat thing. So like a conical entry should be. So these and all factors, like even you have an efficient pump at site, like you buy 85% efficiency pump. So if at all you are not going to see all these things, still your pump will not be an efficient pump operating perfectly. Okay. So now we touch upon the emerging trends in energy efficient pumps. So what you have already seen this, the integrated VFD approach for the market, where instead of having a separate control panel for the VFD, we can have these kind of pumps with integrated VFDs and a controller, and pre-programmed for the pumping application. So I can program the pump for pressure application, temperature application, or level application. So it is pre-programmed. And even parallel operated skits, it can come as a plug and play solution. So it can come as a plug and play situation for variable demand application, varied demand applications. You can have this kind of.
நான் எப்பயும் ஐடி கார்டு போடுவேன், அதுக்கு மேல ஒரு 12 ஐடி கார்டு போட்டுருக்குது.
So in terms of the smart digital dosing for precise dosing, here you have this digital version dosing pumps that can save a lot of chemicals with the precise dosing, and your non-clock wastewater pumps. Here also the situation is so important, in which the surface mounted pumps are properly grouted on the foundation, in which here what we insist to have a auto coupling with the guide rail assembly. So the pump automatically goes and locks on the bottom. It is a self-engaged coupling so that it can come out very easily, and also it can go and rest with a lock, automatic locking feature in it, so that there will not be any leakage from the pump discharge into this area. So this is also possible with a non-clock situation, because we see a lot of demand for sewage or dewatering pumps into the market in the thermal areas, and we can do with this alternate selections. Okay. So the coating or because the normal pumps are being painted for the situations. Okay, both internally, maybe for the external painting happens predominantly. Internal painting is not done. Okay. What is a challenge we can say is, like, over a period of operation, the internal parts get corroded because of varied liquid conditions, pH level variation, TDS, chlorine. A lot of liquid parameter keep on varying from time to time, and that eats away the material. So that once you have a corrosion happening within the material, obviously your life, your efficiency drops, and obviously your life of the product also comes down. So these coatings will help you to save the product. One, what we could offer generally is your electroplated coating, like it is the cathodic electrode deposition coating on all cast iron products, because the impact is seen on the cast iron products. So that is being done both internally and externally, that have a sustained efficiency over a period of time. Yes, there are many corrosion resistance coating which is available, so that we can able to decide and take a call on the product itself. Because if you have a very large pump and you have a challenge of corrosion, obviously you can invest on it and extend the life of the casing. Because if a casing is failed, means the casing is completely corroded, obviously that becomes a huge capex for you. Okay, so that and all you can able to avoid with this kind of coating solutions. Okay, so what we had touched upon is more of individual water application. What we also have is in the market is the automation in your chilled water system requirement. Like in a power plant, obviously there will be a chilled water demand, and based upon the demand, the chiller, the pumps, or the cooling tower is going to operate. So this kind of plant optimizer will help you to take the data of your chiller, cooling tower, pumps, and try to run efficiently all the system, so that your building comfortness is being met, one thing, and also your overall energy consumption is also reduced. So this also a new avenue we can say on the chilled water system approach, where a lot of saving potential is available. I have one case study in which I just want to touch upon and reflect on the options. We have given it for a TNEB Valutur gas turbine power station in Ramanan. So they were using some N-section series high pressure pumps for a desalination plant. So we could able to change it with our vertical multi-stage version pumps. So say from a 55 kilowatt motor, we could able to end up in offering a 37 kilowatt pump set, meeting the same kilowatt rate, means the pump capacities what has been already used. So obviously there is a change in the power consumption close to 18 kilowatt on the motor front. And obviously when you check the power consumption, obviously there will be still another 10% would be lesser in our situations. So this is one example within the power sector we thought we'll reflect. Now obviously power sector have a lot of potential to change smaller pumps, because the smaller pumps population is much higher than your larger capacity pumps. So the volume wise you can able to adapt changing the smaller pumps to improve more energy efficiency in the system, and also your capex also will be very normal, we can say. So I have just concluded this is my last slide for this presentation. So where we could see the avenues for energy saving and also making your product or the pumping system more energy efficient is moving from a throttling valve situation to a speed control, going for a smaller parallel operated systems for variable load situations, adapting energy audit periodically for the older pumps to improve the overall system performance. And wherever possible, you can go for replacement of very old pumps and moving to energy efficient motors. Like you talk about moving from EFF1, now you can adapt straight away to IE3 as a minimum. And even you can still adapt IE4 situations also. Okay, so with this, I stop my presentation. Maybe I'm open for your questions now.
Yes, sir. Participants, any questions from your side? You can discuss now.
Sir, thank you very much, sir, for a wonderful presentation. Sir, this is Jiva. I just wanted to ask you a few technical related queries with respect to Grundfoss bed test facility. For example, in the presentation that we have seen that how exactly Grundfoss does the bed test facility for a particular pump. Do you incorporate all the points that you have explained in the right from the pump section, piping designing to everything, and then you give the then the third party inspection will come and finalize it, and then it will be sent to the customer. How is that the test bed facility and how it is incorporated, sir? That I just one for my interest actually.
Yeah. So you're calling from, sir? Maybe I can note your.
Pardon, sir.
No, you're calling from which place, sir? Maybe.
Yes, sir. I'm calling from. I'm an assistant professor working at Kumaraguru College of Technology, Coimbatore. Earlier, I worked in power plants in. I had an O&M experience and a commissioning experience in from L&T. Now I'm working as assistant professor, but I was not able to go to the test bed facilities, and so I just wanted to know how is that so, because we used to see a lot of test bed reports and all from different pump manufacturers and all. I just wanted to know that how to do that pattern.
Okay, sir. Maybe Grundfoss having a closed loop testing facility at our facility, sir. Okay, so wherein which we test the main parameters, particularly on the pump flow, head, what is the energy consumption. So these are three mostly available parameters we can able to perform it. Okay, so this is been mandate for all the pumps, because when you buy a pump, you obviously look forward on the what level it is been operating. So as a manufacturer, we used to test it and offer to the various things. So obviously ours is a closed loop, a bit automated, where we could able to monitor. We go as per the approved performance standards. So in this case, we follow this ISO 9906 standard for testing. So in this testing, what is the guidelines we have taken in general for the 3B tolerance levels. So for 3B tolerance, what is the tolerance we can able to maintain for the flow, head, and efficiency and power. So that is being maintained as a benchmark. So once your result is within the tolerance, obviously that gives a result stating that pump is okay to go ahead. So this is done in all the pumps, sir.
Thank you very much, sir.
I hope you have the
yes,
answer.
yes, I got it. I got it. I got the things, sir. Another query is like, as a customer, say if I give the flow rate of the pump, this is my requirement. How exactly the design phase you will get it into the data sheet, like the specific data sheet of a pump? You get it right. Like as a customer, if I say this is the flow rate, this is required. How exactly the design phases goes in? Do you have any software to create the data sheet, or how is that done actually?
Sir, sir, if you talk about any pump manufacturer, because in a common forum, I cannot completely be aligned with Grundfoss. So in general, any pump manufacturer will have its own designed parameters reflected in the name of a performance curve and a technical data booklet. So this is one thing. Okay. So in olden ages, like you will find a performance curve booklet where manually we go and see it and select, like you want a pump for say 100 meter cube at 3 bar pressure. I'll go and select a pump which the duty falls in the BEP with all site conditions almost matching. Okay, so this is a manual way, but in new age, all pump manufacturers have their own selection softwares. Some manufacturer is having very closed programs where they don't disclose it. So they do the selection, they give it. Whereas maybe company like Grundfoss or there are some more companies in the market, they are open to the market where we give our selection software accessible for everyone. So our software, like it is named as Grundfoss Product Center. If you Google it, you will able to get that complete tool. So just inputting your flow and head and type of pump. Like now it is like flow and head is a common word. But I need a pump for cooling tower. I need a pump for submersible borewell. I need a pump for sewage. So that defines a type of pump, and you can size the pump on your own. And that sizing tool will help you to reach the highest efficiency pump. So that is the way the programming is done, sir.
Thank you. Thank you for your excellent reply, sir. Thank you very much, sir.
Thank you, sir.
Participants, if you have any queries, you can discuss now. Sir, I think your mic is muted. Sir.
Thank you, sir. Thirumurugan, sir. It was an excellent lecture, sir. I hope the participants would have benefited immensely from the talk. Like having no other doubts, we call for the session. We will post lunch. We can assemble for the third session of the day. Thank you all.
Thank you, sir. Thanks for the opportunity given. And maybe you can reach me for any queries and details needed.
Yes, sir.
Thank you once again.
Thank you. Thank you.
Bye.
Thank you. Thank you.
Participants, please submit your feedback form, which is already shared through email as well as in WhatsApp group. And the next session will resume at 2:30 p.m.